Okay, thank you very much for the very nice introduction, and thanks for having me, and thanks for coming to this talk. So, um, Feel free to ask me questions throughout the talk. So if there's something you have in mind, then just ping me here. I'm happy to answer the question straight away. Um, so what I will be talking about today is not very much about NLP. I will be focusing on our work in speech processing. And here's a list of all the people who worked over the years with us on Wave2Vec. And without them, obviously this work would have not been possible. But before I get started, let me do some shameless advertising. So should you be on the market for a full-time position, a postdoc, or internship, we have offices in various locations of the world, as you can see here. FAIR is like a blue sky research lab where we can work like this. That I will be presenting later on. So feel free to get in touch. Now back to the topic of this talk. So machine learning, there have been a lot of success in machine learning in many tasks, but most of them, or many of them, are definitely supervised setups. So meaning that we require to train the model with input-output pairs. So for example, if you want to identify cats, or objects in images, then we require data where we have images and corresponding labels. But there's two problems, or at least two problems with that approach. So many times the data that we collect doesn't exactly match what we want to use it for, or at least one of the use cases we might use it for. So we might want to recognize the cat in the second picture here as well, but the data we may have collected may not exactly fit that kind of cat picture that you may see. And the second problem is we do need a lot of data for to train our models, and that means we have to annotate a lot of data. So if you map this to the speech domain, and in particular speech recognition, where we want to transcribe speech audio, such as me speaking right now, we have lots of examples of recorded speech audio as well as transcriptions that are usually annotated by people. And if we do that, then or people have done that a lot, and there's a lot of data for the major languages of the world, or a decent amount of data, so on the order of thousands of hours. But we have a lot of languages in the world. There are approximately 6,500 or 7,000 different languages on the planet. And that doesn't even account for dialects. So there's a lot of dialects, and we know there's dialects in big countries, but there's even dialects in small countries. So the country I'm from, with 8 million citizens, there's different dialects as well. And if you speak to a person on one end, you will realize that there's quite a difference than speaking to somebody at the other end of a very, very small country geographically and even population-wise. And then the next issue is also that the way I speak right now is not exactly the way I'll speak on the phone, for example, right? So there's different domains, there's different dialects and many languages, and collecting thousands of hours of annotated data that is requires a lot of effort for all these different domains is simply infeasible. Now, looking at other fields, for example, NLP, and computer vision, one approach that has worked very well there to deal with the lack of labeled training data is to do pre-training, self-supervised training, unsupervised pre-training. These are all the names. And that had quite some success. The performance of systems has increased steadily with better and better models trained on more and more data and bigger models. And we see a similar trend now in computer vision, where there's quite some success with pre-training. So the basic idea of pre-training is to learn good representations on samples where we have no labels. So on just images, on just speech data, just on text or written language, basically. And then to basically fine tune this with a minimal amount of labeled data. And the way this is done in NLP predominantly right now is to occlude parts of the sentence and to get our pre-trained model to basically predict those masked or occluded parts of the sentence. And in computer vision, the predominant approach right now is to make an augmentation to an image and to train a representation that will then be invariant to this augmentation. So basically, we want the model to assign the same representation regardless of whether there is some changes in the color palette or in the background or other type of augmentations that people apply in for this pre-training. So going back to the speech domain, what we would like to do is we simply would like to learn good representations of speech audio from unlabeled speech samples. And when we have done this, and we have a pre-trained model that can assign good representations, then depicting how this would look like here for various applications. So we have like speech audio at the bottom, we have our pre-trained model, and I will talk all the rest of the talk about how this model will look like. We get a representation for the speech audio, and then we would like to, for example, transcribe the speech that, or your when you, for example, dictate something to your phone. And we would basically put a little classifier on top of this representation that the model produces to then transcribe the speech that was recorded. And that's known as speech recognition. Another task that we might want to use the same model for is to translate your spoken language immediately into another language. So I'm speaking English here, but we might want to quickly translate what I'm saying into, let's say, German. And we can directly go from speech to a foreign language, speech in English to a foreign language to do that. There's no speech translation. Another obvious application is that we would like to know what people are talking about, or what is in this audio. Is it music? Is it speech? Is there some background noise and things like this? So we might want to quickly identify what we are dealing with here. So we want to build a classifier that, for example, can identify music or other types of audio events. So this illustrates that if you have like a model that can build this type of representations, then you can fine tune it for or use it for many different speech applications. So what I will be spending the rest of the talk on is to summarize the work of my collaborators and myself on speech for the past, or speech self-supervised learning for speech for the past 2 years. And the outcome of that project so far is that we can build speech recognition systems with a very, very small amount of labeled data. So we've shown that we can build good speech systems with just 10 minutes of transcribed data or 48 utterances. And then I'll also talk a little bit about multilingual pre-training to build multilingual systems. So this line of work started with the original wave-to-back paper, where we were heavily inspired by the CPC work. It's the contrastive predictive coding work, which basically takes a speech signal and encodes it. So here we encode a speech signal with a convolutional net on the top left here. These are the light blue triangles, and then we apply another convolutional net to build even larger context representations, and then we compute basically whether a particular representation in the future, so to the right of the dark blue triangles, is actually really the right next time step, or it's a distractor. So we basically get them all to predict the future, very similar to what people do in language modeling. And we predict the future at various granularities. And these ideas are the same as in CPC, but we simplified them all a lot by making the architecture entirely convolutional, simplifying the loss, and crucially, we also evaluated this idea on speech, automatic speech recognition, so transcribing speech to text. And it turned out that it actually works fairly well, as we can see in the graph down there, where we use actually a rather small data set, the Wall Street Journal corpus, and we compare here pre-training with wave-to-vec to not pre-training, using either just 8 hours of labeled data up to 81 hours of labeled data, which is still not a whole lot, but this was our first step in the direction of working on validating self-supervised learning for speech, and there were some nice improvements on the very low resource setting. The next idea that we pursued was to to try to learn, sorry. The next idea we looked into was to try to learn discrete speech representations. So the speech signal that we process is a continuous signal. We build an algorithm that can identify speech units, learn what are the units in the speech itself by basically quantizing the data on the fly. So we have these very bright green circles here, and that denotes the quantizers. So when we basically summarize some of the speech signal with a convolutional net, we would then assign this representation to a fixed inventory of representations, and thereby assign a discrete label to each 25 millisecond chunk, which is what each one of these triangles encodes. And then we would again apply the same algorithm as before, so summarize the speech into larger representations with these dark blue triangles, and then solve this prediction task of the future. So the crucial idea is that we try to learn these latent discrete representations. And the nice thing about that was that, well, I mean, the way we do it is instead of just having a single discrete representation, we actually have multiple ones sometimes. So for the same times that we assign multiple such discrete representation, which is known as product quantization. And then we use either Gumbel softmax or online k-means clustering to do the quantization itself. And once we have these discrete units, then the nice thing is then you can actually just turn this back into an NLP style problem. So you basically quantize your speech signal, and then you apply a standard seek-to-seek model that you might use for translation or something like this to do speech recognition. Or as in our case, what we did is we just used the standard BERT algorithm to learn representations for the entire sequence and then feed this into an acoustic model. So this is sort of a very quick summary of what we did previously, but our latest work, which is known as Wave2Wake 2.0, combines all these ideas. And what we do there is we jointly learn an inventory of speech units, and then also learn context representations with a transformer network, which looks at the entire sequence at every point. And the way this works is we take the raw waveform at the bottom, we encode it with a convolutional net that builds representations for about 25 milliseconds of speech audio. And then we feed that into the transformer that then builds representation for the entire sequence and builds these context representations at the top. But there's also a second path for those latent speech representations, that is the quantization. So we quantize the speech signal exactly like in the VQ Wave2Wake setup. And then we set up prediction tasks. So we mask some of these inputs to the transformer, and then we get the model to predict some of these masked quantized units. So the way you can think about this is we have a problem where the input is continuous. And we like to set up a discrete prediction task, very similar to what people do, like, for example, in BERT pre-training, where you predict words that are discrete. But in speech, we don't have any discrete units. So what we do is we learn a discrete vocabulary of speech and then set up this mask prediction task. So that's the idea here. But the important thing is that we do both at the same time. We learn the inventory at the same time as when we solve the prediction task, which introduces some challenges. Because this model can easily collapse, but we have a solution for that I will allude to next. Are there any questions at this point? Okay, then let me continue.
Actually, I have one question. So for contrastive loss, usually you have positive and negative examples, right?
Yes.
So how do you draw the negative examples here?
Yeah, let me answer that question right in the next slide.
Okay.
Okay, that's a good question, and we actually spent quite a bit of time on that. So that is actually fairly important, as for all self-supervised learning tasks.
Also about the quantization that you do, is that like with different kernels every time, or like basically are you trying to capture smaller speech units versus larger speech units?
Yes. What we found is, so what we do in this work is we just use speech units always of the same size. They are 25 milliseconds.
I see.
We found that to be a good sweet spot. People have looked into larger ones, particularly the wave to letter folks. I think they looked into larger units. And I think that's an interesting future direction to look into larger units as well. And there's been some interesting work by MIT which looked into units of different granularities and so on. So yeah, so that's definitely that's something that's worth looking into. Yeah.
Thank you. Yeah.
Okay, let me discuss the objective, the contrastive loss, and then we can talk about these negatives that was just asked about. So as I said just before, we want to predict these masked time steps by predicting the discrete latent representation that is behind a masked time step. And the way this is done is by simply computing a cosine similarity, and this loss here, by the way, is almost identical to the Sims CLR loss in computer vision, where we compute a cosine similarity between the context representation, so that is the output of the transformer, and the discrete speech representation, which is simply the output of the quantized CNN at the bottom that builds these 25 millisecond representations. And then we simply contrast this similarity here to similarities with of the transformer output with other possible discretized latent speech representations. So where do these discrete speech representations come from? Well, we sample them from masked time steps of the same sequence, but also from speech utterances, other speech utterances in the same batch. Now, just using distractors from other speech utterances doesn't work so well because the model very, very quickly realizes that, I mean, it's very simple to distinguish one speech sequence from another. And this is why we have the combination of the two. So we found like a combination of that to work very well. Does that answer your question?
Can I ask a question? So have you tried to also sample like the negatives from the same speaker instead of the same utterance?
We didn't distinguish so much on that because we want to be completely unsupervised, right? So we might not know if something is from the same speaker or not. So that could be seen as supervision. Right. But it's an interesting thing to try. It's definitely a much cheaper supervision than using transcribed labels. Right?
Yeah. So is the performance differs a lot, like just randomly choosing the negatives or choosing the negatives from the same utterance? Is the performance really differs a lot, or it doesn't differ that out?
So from my recollection, by the way, we have a lot of these ablations in the back of the paper, but it's not nearly a year. So my recollection of those experiments was that just sampling from other sequences doesn't work very well at all. Just working from the current sequence works well, but I think also sampling, having a hybrid of the two works slightly better. Yeah. So that was my recollection.
I see.
Okay, so now the problem with this loss here, or with this entire thing that I described, is that we jointly learn this speech inventory, and then also try to predict what is behind these masked units based on that speech unit inventory. And a very trivial solution that our model will find almost certainly is to just always predict the same speech unit. So you always assign the same speech unit to every time step, and then your prediction task becomes really, really trivial, right? So you get this kind of collapse, right? And one way, the way we dealt with that in our setting was that we introduced a diversity penalty. So we basically punish, or like we penalize the model for always using the same codes. So we just have like a simple entropy penalty to encourage the model to uniformly use the codebook, which it doesn't do in practice, but it basically makes sure that you don't always use the same the same target for every time step. Sorry. So how do we mask time steps? So I mentioned that. Well, so for example, in NLP, people mask about 15% of words in a sentence, right? Now we found that that doesn't quite work in speech because the data is much more correlated. So if you have, one time predicting the next time step from the previous time step, and then the one thereafter is extremely simple because the data is highly correlated. So what we ended up doing was we just sample a bunch of starting indices and then mask 10 time steps at a time. So that's about 250 milliseconds. I think it's maybe a little bit more, but about that. And spans can also overlap because we sample those indices individually. And what we end up with is for a 15-second sample, about half the time steps are masked. The average span length is about 300 milliseconds, and we found that to be a good trade-off for the model to learn good representations while still managing the task. So after the model is trained, actually, any more questions at this point? Okay, then after we train the model, then we can go back to all these tasks that I mentioned initially. So, once we have that the good representations that we learned in pre-training, then we can fine-tune this model, very similar to how people fine-tune in NLP and in computer vision. What we did in our experiment is for speech recognition, we simply add a linear projection on top of our transform model that projects the representation that is output by the model to a vocabulary. In our case, it is characters. So we just map to 30 plus characters and train this model with the CTC loss, very standard procedure as it's done in speech recognition on the labeled data. And we use we regularize them all with a modified stack augment algorithm. So that's a standard regularization in speech by now. But we do it in latent space because we don't have log-mel filter banks. We work directly in the raw waveform. And then we just add a language model on top of this this entire construct to improve the performance. So very, very standard procedure. Yes. Sorry, I couldn't. Yeah, it was just that.
I think someone exploded. I think it's okay.
Okay. Okay.
I had a question here. So I don't know if you mentioned this a bit earlier, but your outputs from wave to vec, those are fed into the wave to letter decoder, or you said you use the raw waveforms?
Okay. Sorry. So the input to our model is always a raw waveform. So we don't work with log-mel filter banks here. We always work with the raw wave. So as input, that's what we have. But what we feed into the wave to letter decoder is simply the output, so the logits from our acoustic model. So once we fine-tune the model, we have an acoustic model, and then we just feed this into the decoder, which combines these acoustic model scores with the language model scores.
Can I ask a question? So you say that you feed the largest model. You feed. Do you feed the quantized logits or non-quantized logits?
Oh, we just the quantization had actually at fine-tuning time. There's no more quantization. By the way, actually, the quantization is only something we do for training. It is only for us to get this discrete inventory of speech units so we can solve our self-supervised task. Once we're done with pre-training, this entire second path in this graph that I showed that does a quantization and the pre-training loss, all of this is not used anymore. The only thing that's used for after pre-training is the output of the transformer at the very top. And then we get like a vector. I think it's of size 768 for the base model. And we just simply project that vector into a vocabulary of of whatever our acoustic model is predicting. So in our case, we predict characters. We could also be word pieces, just be words, whatever. And this model is then basically, we then continue training this model, but on the labeled data. And then this model predicts a probability distribution over our text vocabulary. And those outputs are then fed into a decoder, which combines those acoustic model scores with a language model.
Okay, thank you.
Okay, so how well does all of this work? So at the beginning, I talked about wave-to-vec, the original wave-to-vec work being evaluated on a sort of small scale setup, Wall Street Journal with 80 hours of speech. And the big question that we're asking in this work is, can pre-training or self-supervised learning also work in a high-resource setup? So when people have like 1,000 hours of speech, and this is for this setup, people use the LibriSpeech corpus, which is a corpus of read audiobooks. So it's fairly high-quality data, publicly available data. And the error rates for this benchmark are fairly low now. So you can see here one of the best models, I think it's not the best anymore, but it's pretty close. The ContextNet model gets a word error rate of 4.1. I think the best model is now 3.9, the best supervised model, excuse me, the best supervised model. And we were interested is, does self-supervised learning work for this kind of high-resource setup as well, where we have a lot of labeled data? And how does it compare to alternative algorithms that also make use of unlabeled data? And the setup we have here is 960 hours of labeled data and 60,000 hours of unlabeled data. And here's the performance of, as I said, this is the best supervised model in gray. And then in black is our model, the wave-to-vec model, when it's trained in a supervised only fashion. So it gets good quality, not as good as the state of the art in supervised, but this is what it gets. And then we add the unlabeled data and do pre-training and compare this to another semi-supervised method, the noisy student method, which is a self-training approach that basically labels the data and then retrains them all. And I'll talk a little bit more about that later, but it was the state of the art at the time, and it's still getting some of the very best results. And what we find is that the self-supervised learning here can perform as well as the best semi-supervised methods in this high-resource setting, and is actually conceptually simpler because we have a two-stage approach where we just basically pre-train and then fine-tune, compared to this noisy student training, which labels the data, retrains, and then relabels in multiple iterations, etc. But the really interesting part about this paper was the low resource setup. So we have a lot less labeled data, going back to the question about how do we build speech systems for all the languages in the world, and so on. And what we find here is, again, comparing performance to this semi-supervised approach that got excellent results. We find that if we use the same amount of labeled data here in blue, we can do a lot better. And if you reduce the amount of data to just 1 hour, we can still do better. So if you use 100 times less labeled data, still, of course, the same amount of unlabeled data, but a lot less of the annotated data, you can do better. And even if you just use 10 minutes, it's not as good, but it's still not too far off from the 100-hour performance. And then if you add more unlabeled data, so instead of using 960 hours of unlabeled data in this particular setup here, you use like 60,000 hours, you can do as well as a setup with 100 hours of labeled data. Right. So the next thing we're wondering is like, what is the how does model performance behave if you increase model size and the amount of labeled data? And here I'm showing the performance of a base transform model. This is a standard configuration that's known from literature with 100 billion parameters. If you use different amounts of labeled data, the more labeled data you use, the lower the word error rate. And the amount of unlabeled data is here is 960 hours. So if you triple the model size, then the error rate goes down by about 20% relative, 15 to 20%. And if you increase the amount of unlabeled data from 960 hours to 60,000, then there's another nice boost in performance. So that shows that these algorithms scale very well in terms of model size and amount of labeled data. Any questions up to this point? Okay, let me show some examples here. So what I'm showing here is the output of the 10-minute model that was trained with 10 minutes of labeled data only, with no language model, with a language model that obviously helps a lot, but just to have the comparison, and then the human annotated transcription for the particular speech audio sample. And what we can see is that if you don't use the language model, of course, the value rate is fairly high, but the model does sort of, get the transcription phonetically right. And then with the help of the language model, it gets actually a good share, most of it actually right of the transcription. So we found that quite interesting. So with just like 48 utterances, the model can actually do a decent job to learn how to spell fairly well.
Sorry, I might have missed this little detail, but when you said you do supervision with 10 minutes, that is, yeah, 10 minutes across all speakers, or is that kind of a personalized model?
Right. So yes. So we used a 10-minute split prepared by the Library Light project, and what that is, they balanced this 10-minute sample in terms of male and female speakers, etc. I don't know how it's exactly balanced in terms of having every utterance being a different speaker, but they took great care in balancing those utterances as well as they could. But it's only 48 utterances, but it obviously doesn't cover all the speakers that are present.
Just to clarify, so this means you adapt your model on 10 minutes of speech and then you run it over all the test set.
Yes.
So it's basically not personalized. That's pretty impressive.
There's no personalization, no.
Yeah, cool.
Okay, so I was talking about the comparison to another semi-supervised method that is based on self-training. And self-training, and so the question we asked ourselves after this work is, are pre-training and self-training, are they complementary, right? They both use unlabeled data to improve model performance, to build a better model. And so I talked a lot about pre-training here, right? So let's look about how self-training works. And in speech, what people do is they take all the labeled data, however much that may be, and train a supervised model. And then they go out and find unlabeled data. So showing you some unlabeled data here. And then they use this supervised model to label that data. And they assign so-called pseudo labels. So they might transcribe it, maybe not perfectly, but now we have a transcription for every unlabeled utterance that we found. And then we take this pseudo-labeled data plus the original human labeled data, supposedly from the supervised model, and we retrain. And then we get a semi-supervised model. And that's pretty much how this noisy student training works in a nutshell, except for that then they also go back and relabel the data again and repeat this process like 3-4 times. So obviously this method also manages to make use of unlabeled data, similar to how pre-training does it. I mean, similar to how pre-training also makes use of unlabeled data. The mechanism is fairly different, but they both have the same inputs, unlabeled data. Except for pseudo-labeling, you also need labeled data, by the way. For pre-training, you don't. But let's not worry about this right now. We're wondering, so are these two methods complementary? Do they learn the same thing? Well, maybe not learn the same thing, but do they have the same effect? And what we did is, well, we did the pseudo-labeling exactly like I mentioned here. And for the pre-training, actually, no, we actually did it slightly differently, sorry. What we did is we pre-trained them all on the unlabeled data, and then we basically pseudo-labeled the same unlabeled data with a fine-tuned wave-to-back model. And then we fine-tuned the model again on the pseudo-labeled data. So we basically followed the self-training approach just in the regime of our setup here. And what we find is that actually this improves performance quite a lot. So clearly the two methods are not having the same effect. And then we managed to reduce word error rate even further, so going down from 8.2 word error rate for 10 minutes to 5.2. Any questions about this experiment?
Do you have the results for just using the self-training instead of combining two?
So we have, yes, we have results for the standard self-training regime. They are slightly worse than what I show here in the green bar. Okay. Sorry, it's in the paper. It is a little bit worse. Okay. But yes, we have that as well. So what we have here is a sort of hybrid. You can think about it. But if you just train a supervised model, we tried that. So no wave-to-back, nothing. We then label the data and then we retrain the model. We have those results in that paper. They're slightly worse than the green bar, but yeah.
Yeah, and is there any way to measure the quality of these pseudo labels?
Yes. Yeah, I mean you can just decode the def set and see how they compare, and yeah.
I see.
I mean, you can also measure them on the training data for the portion where you have the labels. Although you probably have used that already for the initial supervised model, and then I'm not sure how meaningful that is. It's just basically the model regurgitating what it has been trained on.
Yeah, thank you.
What do you think is the reason behind this kind of, I think it's a pretty big improvement, let's say, from this blue bar to the green bar. Is it possible that the self-training and wave-to-vec are actually learning different things about speech, and then when they're combined together, they can kind of compensate for each other's not very good parts?
Yeah, I think it's hard to say what exactly is happening. The two algorithms just work very differently, right? I mean, one basically tries to take the knowledge that you train a supervised model, and then you project, then you label the unlabeled data, and so you basically use the labeled data already in the early on, versus in pre-training you just use it once you have learned all your representations, everything, right? So I think basically there needs to be more analysis and things like this. What we did is here we just really scratched the surface and looked at, are they complementary or not, and the answer seems to be a clear yes. But I think it's very encouraging to see that these two predominant approaches are actually not doing exactly the same thing, which bodes very well for us to be able to exploit unlabeled data even more effectively.
Right.
So short answer is we don't know exactly yet, but I think it's very interesting.
Right. And do you think it depends on the data set that you use, or is it more like a general phenomenon?
So we looked into one data set here, but for the pre-training itself, we looked at a bunch of other data sets. We have like follow-on papers, and I will actually talk about some of that in a second. I would expect this trend to hold across data sets. I don't think this is something that is specific to this data set. Yeah.
Right.
Cool. Then let me maybe show the summary slide of everything, and then move on to the next topic. So summarizing pretty much all the results that I showed here is this slide here is an attempt at that. So in the gray bars here at the bottom are results of some of the best speech results taken from papers with code, sorry. since 2015, and it shows that there has been actually tremendous progress in speech recognition in just the past 4 or 5 years. On this particular data set, the Libre Speech Benchmark, which is one of the most worked on benchmarks in speech recognition. The error rate has gone down from 13 to 2.5, basically. And all these gray bars here, they use 960 hours of labeled data. They may use some additional unlabeled data. Deep Speech 2, for example, uses even more labeled data, but they all use at least 960 hours of labeled data. And what I'm comparing this to here is some of the results from earlier, where we just use 10 minutes of labeled data. And it's very interesting to see how, if you combine pre-training and self-training, and this is the very last result with 5.2 error rate, how that performs actually slightly better than the best system that was developed a year ago, pretty much, in speech, using a lot less labeled data. So I think we have models now that enable us to build good speech recognition systems with very little annotated data, opening up a lot more applications in speech and democratizing this technology a bit more. And also the very best models here, even that the ones that use a lot of labeled data, they are based on pre-training with wave-to-vec. Okay, so unless there are any questions, I was going to talk about multilingual or cross-lingual speech representation learning.
I have a very brief question, actually. So I just hypothesize that confidence means that, so as you said, you are using hard labels when you do the label generation and training. So is confidence value, so the labels are weighted by the confidence?
No, and we just basically do argmax decoding for everyone. So whatever comes out as the argmax, we use as label. We don't do any filtering, none of that. All of these things help, and that's what's being used in prior work like Noisy Student, but we didn't do any of that. If that's what you mean.
The third last model has the description but this refers to confidence. So would you expect that maybe weighting with confidence would help to improve your model too?
Possibly, yeah. It probably would, yeah. We didn't do it because we just wanted to keep things simple, but yeah. Yeah, these data filtering techniques and so on, yeah, they probably would help. Yeah.
I just wanted to make one quick remark. So it seems like forever ago, we did work pretty much along these lines, but trying to use confidence. And we in fact found that confidence was useful. However, the idea was not to use the most confident inputs, but rather sort of the tier below, on the assumption that the most useful data was stuff that you didn't quite know enough to nail it completely. And that turned out to actually be successful in terms of performance.
Yes, I think that makes sense. That's something people have thought a lot about. I've thought about neural nets as well, with labels moving and so on. And I think that could be an interesting extension of this. We just didn't have a chance to look into it. Yeah.
Let me throw in one more thing, which is, again, rather ancient, but the goal there was to also basically see how far down can you reduce a large corpus and still get good performance. And it turned out if you basically did phonetic sampling in the sense of making sure that you had all phones and all triphones, I think, represented at least once in the data that you used. And this would be stuff that might be contained in individual utterance. You could in fact build systems with about 1/5 of the data that gave you the same error rates. But in any case.
Yeah, I think the folks who have been reviving self-training for speech, or some of them that we worked with on this project, they actually did a little bit of work in this direction, but they sort of didn't use all of the pseudo-labeled data. They only use some of it based on some of these intuitions. So yeah, I think that's a very interesting direction, absolutely, because using all of that data is very laborious to even automatically label. So yeah.
Exactly.
Yeah, and if you do multiple rounds, as has been done in this noisy student training, 60,000 hours, yeah, that's very intensive. We just did a single round in our case. Again, if you do more, you can probably improve those. This result, it is 5.2, but we didn't do any of that yet. So yeah, actually, we might have done it for the camera ready now. Sorry, will be coming through. Yeah, there might be a slight improvement. Okay, so let's move on to the last topic, so we don't run out of time. So cross-lingual training. So far, we've been all in the monolingual world talking about English, but English doesn't cover the entire planet. And we also would like to be able to transcribe data or build speech applications for the languages. And the question then obviously arises, why would we want to build representations that for multiple languages at the same time, so-called cross-lingual representations? Well, oftentimes, if you have little amount of labeled data, we also often have not too much unlabeled data. So if you think about the endangered languages of the world, we probably have next to none labeled data, and also not too much unlabeled data. So the idea of cross-lingual training is that if we train all languages at the same time, then we want to leverage the knowledge that has been built from high-resource languages for low-resource languages, most likely related low-resource languages. And the goal is to improve the performance on low-resource languages. And the nice thing about training on multiple languages at the same time is that we can ideally, hopefully, build a model that can deal with all the languages of the world. That would be sort of the North Star goal here, really. Instead of having one model for every language where we have to relearn a lot of things about how language works in general. Now, this seems a bit far-fetched, but looking at other areas like NLP, there have been great strides recently in multilingual systems. So for language understanding, there have been quite some progress in with pre-training on cross-lingual understanding tasks. Similarly for multilingual machine translation. So we recently had a project where we basically trained a model that can translate between 100 languages, so covering 9,900 language directions in a single model, and that benefited low-resource languages very nicely. So how do we do this in pre-training with Wave2Vec? Well, the simple method we pursued was to simply just pre-train on data from multiple languages. And doing this actually, we found, and I will show you that later in graphs in more detail, is that these discrete latent speech units that we learn during the training, some of them, we find that they're actually shared across languages. Some of them are not shared. And what we also find is that the sharing is more pronounced in languages that are related. And that's a nice finding. I will detail a little bit more in a second. But back to the topic of improving performance on low-resource languages through this cross-lingual training. So here we had a study where we trained, I think, on 10 languages of the Common Voice benchmark, which is read speech, that is available through the Mozilla project. And what I'm showing here in the first set of bars is the performance when we just pre-train on a bunch of, on each language individually of these 10 languages. And we can see that the performance for the high resource languages is pretty good. So we have a very low phoneme error rate, versus the performance for the low resource languages is actually not so good. Now, if we do train all these languages together in the XLSR approach, which is Wave2Vec trained on 10 languages at the same time, we can see a marked improvement on the low resource languages, but unfortunately a degradation in the high resource languages. But that can be remedied by simply increasing the model size. So we triple the model size. So we assign more parameters to this model so it can represent these 10 languages better. And then we can close most of the gap to the monolingual training. And on the Babel benchmark, we can see a similar trend. Another thing we can do is we can actually take this multilingually pre-trained model and then fine-tune that model for several languages at the same time. And then we have a model that can actually transcribe 10 different languages, and that can perform nearly as well, or can perform actually as well as fine-tuning for each language individually. Are there any questions at this point? Okay, then let me move on to, I think, one of the last experiments. So we're wondering, how important is it with which other language you pre-train to improve performance at your target language? What we found is something that is very intuitive, that if you pre-train with languages that are more similar to your target language, then that it improves performance more. And the experiment we have down here was that we simply pre-train on 5 hours of Italian and then fine-tune with 1 hour of Italian. And then if we add another 50 hours of unlabeled data in another language, what is the effect of that? So if you add 50 hours of Italian, obviously that improves performance the most because it is the most similar data to our target domain. Spanish is the next best, then it's German, English, Russian, Kazakh, and Chinese. So this ordering makes intuitively sense. Might not be entirely perfect, but it sort of shows that this transfer between similar languages does indeed happen.
Well, maybe this is a stupid question, but is there any way to measure the similarity of languages? So so of course we know that Italian is the most similar with Italian, but how do we differentiate like Spanish and German to Italian? Geography or?
So Spanish is from a linguistic perspective is definitely more similar to Italian than German. So they're the same type of language family, Spanish and Italian. German is obviously, you know, it is clearly is more different than Spanish to Italian. I think linguists would agree on that.
Yeah, so yeah, the first 5 there are all related in their origin. They all come from Proto-Indo-European originally. I'm a little surprised actually that Kazakh and Chinese aren't more different, since they're quite a bit less related, I think, than the other ones. Yeah, one thing I was wondering is actually if there's some way to measure the phonetic similarity, because this is mostly phonology, right? There's not really any syntax or anything.
Yeah, I mean, I think you know about the magnitude of the difference. There's another factor going on as well, right? So we pre-train on 5 hours at the very first bar, right? Which is very, very little, right? So I think one additional effect that is happening at the bars on the right is obviously the language similarity that I mentioned, but then the other effect is just adding more data, right? Just adding more data.
Right.
So, and that might impact the kind of, you know, magnitude of differences.
Right.
So
I have a question.
Yes, please.
So here you're showing with 50 hours of Italian, but in your experiments, did you see like how much did it improve with 10 more hours, 20 more, and maybe all the way to 100 hours of Italian if those were available? And did you see, I mean, did you select just 50 because that's when you saw that the curve was just flattening and you were not getting any more improvement?
I don't think we did such detailed experiments here. We just wanted to, you know, look at the effect mentioned above, which is language similarity, and not so much a demand of training data. We did some experiments around demand of training data that I showed in the first part. maybe not as controlled as you mentioned here, but we compared like 960 hours to 60,000 hours, and there was a clear difference. And that was the multilingual case.
So one important aspect that we found in our studies in cross-lingual and low resource was that there is an aspect of speech domain, speaking style, right? So like, for example, common voice is read speech, whereas Babel is conversational speech. So did you do like a study in a cross-domain scenario as well? And
yeah, I think that's that's a very interesting future work. So we're looking some of these aspects actually right now.
In fact, one interesting thing that we found was that it's better to have it's more important to have same domain data rather than language similarity. So if I take Babel for instance, and I can use switchboard, which is also a conversational speech, and in that scenario, like our study was showing that okay, language similarity is not really important, but go for domain similarity when you're trying to adapt quickly. And yeah, I was wondering if how wave2vec does cross domain, and yeah.
Yeah, we haven't. This is an effect we haven't studied in detail yet. I would expect that if the domain of the pre-training data matches the domain of the target data, that is helpful. But yeah, I think that would be definitely some interesting future work to look into. Yeah, particularly because you might have unlabeled data in your target domain, but you might not have labeled data, right? So yeah.
Because I feel that the reason why like Chinese and Kazakh had such an improvement was actually due to more in-domain data, although it's a different language, but the speaking style would remain the same. And like that could be an explanation for this reason.
Yeah. Although as I said earlier, it's like we're dealing with a very, very small amount of data here. This is an ablation. We didn't really scale up very much here. We just wanted to, understand the above effect. Yeah, that would definitely be very interesting to look into in more detail. We didn't have a chance to do that yet.
Thank you.
Thank you. Okay. So the last thing I'm going to talk about is really just analyzing this discrete latents that are learned during pre-training. So what we wanted to understand is that at pre-training, we learn these discrete speech units. And when we have multiple languages, then these discrete speech units, they are actually, the same speech units are being used for different languages. And we wanted to understand, is there some sharing going on? Or are these speech units, so we have a fixed inventory of about about, I think it's 100,000 units or something that we use on average. And are those partitioned into 10 different languages? So we have 10,000 for each one of them, or is there some sharing going on? And the way we analyzed this is we just took data in each language, not the same data spoken, the same data spoken in the same test set spoken in different languages, but just the different def sets. Obviously, they contain different utterances, etc. And we computed the discrete units for them, and then we looked at how are they related? Are they using the same type of unit? And then we visualize this with a PCA plot here. And what we can see is that there are definitely some trends that certain languages cluster together in this space, i.e. they use similar units. The clustering is not perfect, of course, right? So you can find some outlier examples, but this is what happens when we provide the model with no supervision whatsoever. This is how it basically decides to partition how to learn these units and how to use them for different languages. So there's clearly some trends going on that languages that we think are related are using similar type of units. Any questions about this before I conclude?
So actually, I have a diagnostic question here. So this is really, really interesting work. But so I assume that here the clusters are only built on speech and not on silence.
Yeah, silence is about everything. Everything is being the entire utterance is being discretized. Yeah.
Yeah, but your model also has to learn silence or somehow to
yes,
when
it has to learn silence.
Did you do a similar analysis like this one and figure out whether certain silences cluster together in groups of languages?
No, we didn't do that. We didn't do that. That would be interesting.
It's a kind of a diagnostic thing to just check if actually silence is really kind of unique, how to say, universal, right?
Yeah, the model actually assigns a surprisingly large number of different units for silence. What we find, so it is not that we just learn a single silence token. I think we have some analysis of that. We have a plot of how basically the model what kind of units it uses for different phonemes. I think we have a plot at the very end of the original wave-to-vec paper, and the model actually uses a surprisingly large number of those units to explain silence, because it is actually one of the most frequent things we see in the data.
Yeah, and silence actually is not really just one thing. There can be so many different things, especially things that you don't have labeled, right? Like door slams and these kind of things that might happen.
Yeah. Any other questions before I finish? Well, maybe I just finish and then we can think about more questions. Okay, so in summary, so this is sort of the first time that pre-training has been shown to work very well in low and high resource high and low resource labeled data setups. And now we can build like speech applications for very low labeled data setups, which is nice. Cross-lingual training can help low resource languages even more. The sort of two predominant approaches to using unlabeled data in speech appear to be complementary empirically. We have algorithms now that are very, very data efficient, and hopefully this will enable to build speech applications for many more different languages, domains, etc. And if you would like to play around with these algorithms, then we made the code and the models available on the FASIC GitHub repository. And since yesterday, they're also available on Hugging Face, so even more easily. So what's next? Well, some of the future directions here we actually talked about in our discussions throughout this talk. So it would be interesting to figure out what exactly is learned in the different layers of this model, right? So these models that we have, they're like transform models with 24 layers sometimes. So interesting to see what is exactly learned at each layer. There has been a lot of work on understanding BERT in NLP. And the same will happen in computer vision with all these models as well, if it hasn't already. Learning representation at different granularities. I think somebody asked me about that. And then the next frontier that I see is like, can we learn speech recognition models without any supervision at all? So we managed to reduce the amount of labeled data to 10 minutes. But what about if we can lower the entry barrier to 0 in terms of annotation at least? That would be interesting. And can we use these representations that are learned here in the self-supervised way to generate speech? So far we've been working on understanding speech, like speech recognition and so on, but can we also generate? And I think I see the first follow-on work here that actually is attempting to do that has been recently released. Okay, let me thank you to all my collaborators without whom this would have not been possible. And if folks have any more questions, then I'm happy to answer them.
I have quite quick question. So speaking about similarities of languages,
what about languages that have a very similar phonetics, but very like totally different alphabets? So for instance, Ukrainian and Polish languages, they sound like really close, and you can understand other language if you know one of those, but the alphabets are completely different.
Sorry, what is the particular question that you have in mind there?
So like, can those labeled languages still be used in terms of that those languages are similar in their phonetics?
So is your question whether you could have a single model that can still process both of those?
Yeah, something like this. Or like pre-train on one language and then train on another language, but using the labeled approaches.
Yes, to have like sort of transfer between languages. Yeah, actually we did try something like this in, I didn't have a chance to talk about that, where we basically pre-train on a bunch of languages, and then we have an unseen languages for which we have labeled data, and then we fine tune on that. And the approach still seems to work for this. Now coming back to your original question about mixing similar languages, I think the answer is, I don't know about very, very similar languages, but the one effect we definitely see is if you add similar languages, that is actually helpful for both of them, because the model can learn much better from data that is similar to other language. You can use languages, can use the information from language B to improve performance of language A, and vice versa, as we've seen in this Italian experiment that we talked about. Yeah, but I'm not sure if we have looked into exactly like these. I would have to check if we have this particular setup that you mentioned. I think we might actually have that setup, but I would have to check again in our experiments.
Yeah, thank you.
Can I ask question about more about the computational, the budget to train the model?
Yes.
Can you explain how much you need to make it trained?
Yeah. So I think the pre-training is a lot more expensive or a lot more intensive than the fine-tuning. So once you have the model pre-trained, the fine-tuning is actually is relatively it doesn't require as many resources. So for the pre-training, we trained our models, I think, for on quite a lot of GPUs. So the biggest models are trained on I think 64 or even 128 GPUs for I think maybe 4 days or a week. I would have to check exactly again for these particular models here. The smaller ones can be trained faster. Having said all of this, it would be interesting to see, if these models, to make those models more efficient. And I'm very, very confident that this can be all made much more efficient. If we look at like NLP, for example, there has been so much work on making like BERT-style models more efficient. And these are just pretty much, they're very similar to BERT models, right? So I think the same tricks would definitely be go a long way here as well. We just didn't have a chance to look at that yet, but I think that's an interesting avenue for future work.
Sounds good. Yeah, thank you.
So do you recommend, if we wanted to get started on something like this, to fine tune like one of the multi-language models versus training our own?
I mean, yeah, it's very easy to just download the models that we made available. So they're already pre-trained. This is all after all this training that I mentioned. So yeah, starting from something like this, if it works, well, I don't know your particular application, but that would definitely be, I think, a good first step. Yeah.
I see. Like fine tuning to like a new language.
Or depending on what you want to do. But yeah, I mean, you can just take, for example, these English models. The really big English models that I talked about with 60,000 hours and 300 million parameters, those same models have been used for multilingual speech translation. So people actually use them for multilingual setting and get some really, really nice results. So that I can send you the paper later, but yeah, so that people got some very nice results with that, even though this model hasn't seen a foreign language yet.
That's pretty interesting. Is there any future research direction? I mean, aside from efficiency, to like work on like kind of with RNN transducers, like to stream speech, or is this just going to be like one time?
that would be interesting as well. I think these models, as they are not streamable, right? Because they look at both left and right contexts. But it would be interesting to see how this approach can be adapted for like left to right processing, as you mentioned, bar and NP. Yeah.
Awesome, thank you.
Cool. Any more comments, questions?
On the topic of similar languages, what about dialects? Have you tried any fine grain like English, American versus British English, or even regional dialects for a given language?
Getting this data, public data is it's hard, right? But it would be very interesting to do that. I actually believe that this is something that could be very, very interesting, just because there's so many different dialects. Even you say British English, right? Now I spent a lot of time in Britain, but there's a lot of dialects there as well, right? It's not just this is one dialect, right? So I think these methods can be particularly effective for that, because there's so much variety. It's such a long tail, right, of variety, and you just will never have like thousands of hours in each one of them. So yeah, I think that would be. You haven't tried it, and it would be very interesting to see what can be done there.
I actually have a comment about this. Actually, in the accented speech recognition challenge the last year, the winning system is actually using this Web2Vec 2.0. So it's already showed the effectiveness of the accent speech and dialect.
Sorry, which system did you mean?
Yeah, there is an accent speech recognition challenge in the last year, and I forgot the name of the team, but anyway, the one team in China, they actually using the pre-trained model in the FairSeek, and then fine-tune to the accent speech, and then they win the challenge. So.
Okay.
Yeah.
Yeah, if you could send me a pointer, that would be great. I would be interested to learn more about that. I didn't know about that actually. So yeah.
Will there be a recording of this seminar available?
Great.
Well, the recording will be available.
Okay. Do you know where we can find it?
It's on the website, on the seminar website, if you know.
Okay.
Where it is. All right. Any other questions or comments for Michael? Cool. All right. Let's thank Michael again for this fantastic talk. Maybe some applause for me. Yeah, it's kind of weird during this virtual time. I wish you could be at CMU. So just as a reminder, we're meeting again the same time next week. We're gonna have Will Grathwell from University of Toronto talking about some recent progress in discrete sampling and energy-based models. Okay, well, thank everyone, and Michael especially, for attending the seminar today. Cool, cheers.
Thank you, everybody, and thanks for all your questions.